And we're back. And this is P-Dog Does Science, back with the lecture 17.2 on calorimetry and measuring enthalpy changes. And so we left off with discovering what specific heat was, and the Q equals mc delta T equation that allows us to measure. Remember, the Q equals mc delta T equation, which allows us to measure how much heat is flowing into or out of a system. So calorimetry is the actual technique that is used to measure the heat flow in a lot of chemical processes. In calorimetry, the heat change of the system is equal to the negative heat change of its surroundings. So let's write that in a different way. The change in the heat of the system equals the negative heat change of the surroundings. Okay? Or another way of looking at this is that the delta H of the system plus the change in the surroundings equals 0. In other words, that however much one of them changes, if one goes up, the other one has to go down to the point where there is no heat added to the system. And this is just the law of conservation of energy. And let me write that a bit clearer, because that is just really ugly. That is the law of conservation of energy. All right, now when we do this, we use a particular device, and the device that we use to perform calorimetry is the cleverly named calorimeter. So we use a calorimeter to perform calorimetry. And it usually contains water, whose temperature change determines the amount of heat flow, which sort of makes sense. So the Q equals mc delta T of the water is going to tell us what our change in heat is. Now, we then have enthalpy, which is the heat content of a system at constant pressure. Now, the enthalpy will tell us how much heat is actually stored inside the system, inside either the system or the surroundings. So, for example, even if you have something very, very cold, like, say, liquid nitrogen, it is quite cold. It's about 73 Kelvin, or negative 200 degrees Celsius. Even so, that 73 Kelvin is still a significant distance above absolute zero. And so the enthalpy of that system is just like Q equals mc delta T, except the heat of the system, the absolute heat of the system, equals the mass times its specific heat times just the absolute temperature in Kelvin, because that temperature is the difference between 0 and its current temperature state. And that whole thing is the enthalpy of your system. Well, that's a really esoteric way of looking at it, that it's kind of overly complicated to think of it that way. But what enthalpy really does, what we really use enthalpy for, is to examine the change in the heat. And so the heat change of a reaction is the same as the change in the enthalpy, which is symbolized as delta H. All right, so when this undergoes a chemical reaction, that we have a temperature before and a temperature afterwards, the delta H starts to equal mc delta T, and the Q that we measure in our calorimeter is equal to the change in the enthalpy, which gives us the change in enthalpy of any chemical reaction, if it takes place in the calorimeter, equals mc delta T of the water. So that if this water actually equals negative, that if this water temperature, as this water temperature increases, Okay, and this Q increases. Q, not G. If this Q increases, that means that the system has lost energy. Because it's gone from here into there. Okay, and that brings us to our thermochemical equations. How do we study this, and how do we show, when we write our equations, that this is actually what happens? Okay. In a chemical equation, the enthalpy change for the reaction can be written as either a reactant or a product. It can fit on either side of the reaction. So an example would be calcium oxide reacting with water to form calcium hydroxide and a release of energy. If it releases the energy, if we have a release of energy, it should be then exothermic, and that's what we get. Now, here's how we write this. And I'm not sure why that's not erasing, so I'll take that. Calcium oxide plus liquid water. Calcium oxide reacts with water to form calcium hydroxide and a release of energy. So if it is written in the equation as in this case it would be a product, so a product of this reaction, okay, this will show that it's an exothermic reaction. However, if we write just the reaction, and then we indicate how much heat, the delta H is going to be negative because it's going to be going to the surroundings. It's leaving the system and making the surroundings hotter. Okay. Our next example is baking soda. Okay, baking soda, which is sodium bicarbonate, decomposes into carbon dioxide, water, and sodium carbonate when it is heated, and it is heated with an endothermic reaction. And so when we write this one, we have baking soda decomposing, this is baking soda, decomposes into carbon dioxide, water, and sodium carbonate. Carbon dioxide, water, sodium carbonate. When it is heated, which means that these 129 kilojoules are added to the reactant side, and when we heat it up, it becomes sort of like a reactant in the reaction. Okay. So if it adds over here, because in the chemical equations we only add things, we never subtract things. Or if it's endothermic, then we have this sodium bicarbonate decomposing into sodium carbonate, water, and carbon dioxide with a delta H of 129 kilojoules, which means that this is positive and it goes into the products of this reaction. And so this heat comes from the surroundings. Okay, so this is what our equations look like with exothermic and endothermic reactions. That our delta H would be positive for an endothermic reaction because that's how much our products, that is the change in enthalpy, that is how much we have increased our heat within the system, how much energy the system has absorbed. If it's negative, then it is a decrease in the enthalpy. It is how much our products have lost in chemical potential energy and has heated up its surroundings. That's it for 17.2. Pretty quick. And we'll see you next time for Heat and Changes of State with 17.3. P-Dog signing off.